Lesson 47. Fundamental Theorem of Calculus, Part 1, Riemann Sums, and the Definite Integral, which the definite integral is essentially fundamental theorem of calculus. Stay a second.
Third. Or wait.
The second.
Oh, okay. I was confused.
You had me confused when I was like, wait a minute, did I lose a day in here? Whew, okay. Fundamental theorem of calculus. When we talk about what's called the fundamental theorem of calculus, it is a way to work with integrals when we have boundaries. Okay? We're used to working with integrals when we're basically just taking the antiderivative. We're taking the antiderivative and we're putting a plus c on it because we don't really know for sure. There could be another constant at the end that took the derivative of and became 0. We don't really know. But fundamental theorem of calculus is, okay, how do we deal when there are definite boundaries? Okay? It's kind of like when you take a derivative and you're trying to evaluate it at a certain point, except here it's integrals, and we're evaluating them in a range. So how this reads is the integral of f of x dx from a to b. And how we evaluate that is you do capital F of b minus capital F of a, given that f of x, capital F of x, is the integral of lowercase f of x. Okay? The idea here, and I'll take you through several examples, but what we're doing here is we're taking the integral, so we're still going to take the integral or antiderivative, whichever you want to call it, but then we're going to plug these values in. Plug in the upper value, plug in the lower value, and subtract those two quantities. Okay? And again, I'm going to work you through this. Now, when I say derivative, your brains go and think slope, I hope, right? When I say integral, your brains need to go and think area. Okay, so when we talk about an integral, it's the area under the curve is what we usually say. Or, in other words, the area between the graph of a given curve and the x-axis. When we get fancier, it will be the area between two curves. But if you're only just given the one curve, it's the area between the curve and the x-axis. When we've been doing area under a curve, and we've been doing our summing of the rectangles, right? And then we did our infinite summation. That's what this is leading up to. Okay? This is leading up to area under a curve. So let's look at example A. Example A says find the area. So when you hear find the area, we're going to think integral. Find the area under the graph of f of x equals 4 sine x between 0 and pi. So basically, you could sketch the curve of sine, 4 sine x, from 0 to pi, which would basically be that first mountain. I want to say hump, hill, mountain, whatever you want to call it there. Okay, it's that mountain from 0 to pi. We want the area under that. Now, in order to find the area under that, area is integral. So we're going to set up the integral here. It's the integral from, what are the boundaries they're giving me? 0 to pi. Traditionally, your smaller boundary goes on bottom. Your upper boundary goes up top. Okay, occasionally they're switched and there's rules for that. We'll get to that later. This is find the area from 0 to pi of 4 sine x. And then because it's an integral, we always have to tack on the dx. So that's the problem we're trying to find, or trying to solve here. Okay, start off like normal. What's the integral of 4 sine x? He says it with a question in his voice, of course. We're going to ditch the plus c for today because we have these values instead. Okay? Then I'll talk about that. So in other words, you still agree with his negative 4 cosine x? Okay, and I agree with it. So Okay, so the integral of 4 sine x is negative 4 cosine x. Okay, evaluated from 0 to pi. So Trevor asked about putting the plus c on. I'm not going to put the plus c on because I have values to plug in. So we're going to say, I read this as evaluated from 0 to pi. Okay, we don't need that plus c because we have values, is what it comes down to. Now, this is the part, we've already taken the integral, we're plugging in these values. So what we're doing is negative 4 cosine evaluated at my upper boundary, so pi, and it's going to be minus negative 4 cosine evaluated at my lower boundary of 0. So let me write that out for us. Negative 4 cosine of pi minus negative 4 cosine of 0. So we have to know our trig values here. Negative 4 times, what's cosine of pi? Negative 1 minus negative 4 times cosine of 0. What's cosine of 0? Positive 1. And that's the math you're doing to finish this up. Negative 4 times negative 1 is 4. Minus negative makes it plus. And 4 times 1 is 4. So 4 plus 4 is? Nice try. 4 plus 4 is 8. 8 what? Because we're being asked to find area, I'm going to say 8 units squared. Okay, questions about what we did there? Okay. We are working with definite integrals today. They are definite integrals because they have boundaries, which means when we get down to the end, our answer is just going to be a value. I would say a number, but yeah, a number, a value, as opposed to indefinite integrals when we don't have the boundaries and we have to tack on the plus c. Okay? Okay, so let's try example 2. Evaluate the integral from 1 to 3 of x squared plus 2x plus 5 dx. So start by taking the integral. Okay, integral of x squared.
1/3 x cubed.
1/3 x cubed. You add 1 to the power and divide by the new power. So 1/3 x cubed, or x cubed over 3. Plus integral of 2x. Add 1 to the power, divide by the new power. Makes it x squared. Plus the integral of 5. 5x. I'm not going to put on a plus c because evaluate from 1 to 3. Because this is more than one quantity, we tend to use brackets around it and then put the 1 and 3 after the value for evaluation. The previous one, it was just one quantity, so I just used a bar to show my evaluation. Here, because it's 3 quantities added, we put the brackets. Okay, so what am I doing here? Okay, so we're going to plug in 3, get that value, and then minus, and we're going to plug in 1. Okay, so I'm going to write it out, and then we can do this. So 1/3 times 3 cubed plus 3 squared plus 5 times 3. We're going to get that quantity, right? Minus, always minus, then we're going to get this next quantity. So 1/3 times 1 to the third plus 1 squared plus 5 times 1. And that is the math we're doing here. There is importance in being able to do this type of problem without a calculator. Okay? I mean, not that you can't use the calculator in certain, situations and stuff, but this is doable math without a calculator. 3 cubed is 27. 1/3 of 27 is 9 plus 3 squared. So 9. 9 and 9 is 18 plus 5 times 3, 15. So that first parenthesis is at 33. 18 and 15 minus 1 cubed is 1. 1/3 of 1 is 1/3. 1 squared is 1. 5 times 1 is 5. So 1/3 plus 1 plus 5. Yeah? Yeah, my brain was going 6 1/3 for the moment. And, I mean, here's what it comes down to. What are you most comfortable with? Because somehow you have to get an answer, although usually calculus does not want a mixed number answer. So, if we're going to say that this is 19/3, what do you know about 33? 99/3? 99/3 minus 19/3. 80/3. 80/3 what? Units squared. Again, it's not that you can't use a calculator there, but there is value for being able to work what we just did without the calculator. Okay, but that type of problem is, a good multiple choice type AP problem on the non-calculator portion. Okay, one more in this section. Evaluate the integral from 1 to 2 of 3e to the x plus 2 over x plus x squared dx. Okay, what's your brain doing first? The integrals. What's the integral of 3e to the x? 3e to the x, yes. Just remember, derivative and integral of e to the x is just e to the x. Plus integral of 2 over x. Excuse me. 2 natural log of absolute value of x. Remember, 1 over x, the integral of 1 over x is natural log of x. Officially, it's absolute value because you can't put a negative number in there. In this case, we'll only be putting positive numbers in, so not a big deal, but plus integral of x squared. One-third x cubed. Evaluated from 1 to 2. Again, I'm using the brackets because there's multiple terms here. Okay. So, fundamental theorem of calculus, which is what this is today. I know I tend to forget what it is. I know how to do this, but I tend to forget this is called fundamental theorem of calculus. So if you're told using the fundamental theorem of calculus, it's just evaluating the integral. Okay, what do we start off doing here? Plug in 2. So 3e to the x, plug in 2 is going to be 3e squared plus 2 natural log of 2. You don't necessarily have to write the absolute value once you plug that in because it is positive. Plus 1/3 of x cubed. 1/3 of 2 cubed. Okay. I'm going to put that whole value in parentheses. Remember, you are subtracting, and now we're going to put 1 in. So 3e to the first plus 2 natural log of 1 plus 1/3 times 1 to the third. Okay. Again, this kind of depends on, is it a calculator, is it not a calculator problem? There is some cleanup we can do without a calculator that would allow you to express your answer in a more simplified form, but still not using a calculator. And then we can also use a calculator to get to your decimal answer here. Let's clean up what we can. Let's see, 3e squared is 3e squared. There's nothing you're doing there without a calculator. 2 natural log of 2. 2 natural log of 2. Officially, it could become, if it needed to, natural log of 4. Okay. I don't necessarily know which is more simplified. It just kind of depends. I'm going to leave it as 2 natural log of 2 here. Plus, what's 1/3 times 2 to the third? Not 4/3. 8/3. Okay. Minus, let's go ahead and get what we can from the next one. 3e to the first. Just that, 3e. So I'm going to say minus 3e. Do your brains know this? What do you know about natural log of 1?
0.
It's 0. So what's that mean about that whole term? It's all 0. Okay. And then 1/3 times 1 to the third is 1/3. Now, keep in mind if I'm removing these parentheses, we're subtracting everything from the second parentheses, so it is minus 1/3, correct? There is a small bit of cleanup you can do if you're not going the calculator route, and that is the fact that 8/3 minus 1/3 is 7/3. So I could give this answer of 3e squared plus 2 natural log of 2 plus 7/3 minus 3e. Depending on the given scenario, that is an equivalent answer. You can also plug it into a calculator, yes? Did anyone plug it in and get a calculator answer?
That was 1.732.
17.732. I have written down 0 after that, so the fourth value must be a 0. So 17.732, 0 if you want, labeling of units squared. Now, I am trying to remember, when do I introduce the calculator version of this? Or do I do that today?
Fundamental theorem of calculus 2.
I don't know. That's what I can't remember. My brain is blanking. Okay. Lesson 53 is when I introduced the calculator version of this. Okay, so I don't need to introduce today. What I'm getting at is you can plug this exact problem into your calculator and it will give you the decimal answer. Okay, which is on the calculator version of on the calculator portion of AP a valid answer. You would not have to work this, show all this work if you just need a decimal answer that would then carry forth to something else, is what would usually happen. Okay, so, but I don't officially introduce that today, so. Okay. Riemann sums. I'll be honest. This lesson just barely touches on Riemann sums. We will talk more about Riemann sums later in the school year when we talk more about AP examples and stuff. I don't do much with it today. But just to give you a little bit of the history here, two mathematicians, Riemann and, I forget, is it Cauchy? I forget how you say it, came up with is what is called a Riemann sum. Instead of using upper sums and lower sums, they defined a single sum. Okay, so remember we were doing the upper, the lower rectangles, those type of things. They defined a single sum. For this sum, any point in a subinterval can be used to determine the height of a rectangle drawn on the subinterval. The widths of the rectangles can be different. So say we have n different subintervals. The Riemann sum would be as follows. And keep in mind, this is what we were doing where we had delta x. We did delta x, which was the width of the interval. And then it was times, and we just did all the heights added up, right? Which was always the f of x. So f of x1, f of x2, f of x, all the way up to n. So that's what that's saying here. That's where we normally factor out the delta x, and then times all the heights added. Where f of x values are the heights at x of n, and delta xn are the widths. Now, the limit as p approaches 0 of the summation from I equals 1 to n, so the summation of all of those, of f of x sub I times delta x sub I, is equal to the integral from a to b of f of x dx. Okay, so this is saying the summation of those widths times those heights, right? The limit as p approaches 0 of that limit, of that sum, is equal to the integral from a to b of f of x dx. Okay, and do notice here that p approaches 0, it says means the norm of p approaches 0 as n increases with outbound. Okay, which that takes you more into a statistics version. I want to, yes, it's on the next page. Okay, we're going to look at example 4, and I'll give you some basics here. Now, let me write down what was on the other side, the forming, except I'm going to use the limit as n approaches infinity, summation, from I equals 1 to n of f of x sub I times delta x. Okay, that is the overall format of a Riemann sum. Okay, and then the fact that that's going to equal the, my words aren't here, oh my gosh, the integral. Okay, now, a couple of things. In order to fill this in, we're going to have to know delta x. Do you remember how to find delta x? How have we found delta x in the past? Yeah, officially we always said it was officially b minus a divided by n. Because you, in order to find the width, you know, a lot of times it's just going 0 to something. But find the width, so you subtracted your endpoints divided by n. Well, in this case, as you look at the example, what do you think my b and a are? 2 and 0. So it's 2 minus 0, and it's divided by n, because keep in mind, do we know how many intervals? No, we don't have that. And so my delta x that I'm going to be using here is 2 over n. The other thing we need to know going into this problem, you guys remember talking about x of I when we were doing the infinite summation charts? Remember how we found x of I? X of I is delta x times I. So in this particular problem, my x of I is going to be, well, what's delta x? 2 over n, and then times I, because I just represents what, first interval, second interval, so on and so forth. 2 over n times I can just be written as 2i over n. That's what we're going to use as x of I. Okay, with that given information, we're trying to express this integral here from 0 to 2 of e to the x dx as a Riemann sum. So Riemann sum, we're going for this form over here. Always going to start off, limit as n approaches infinity. The summation. I hate to use the word always. In fact, I can't use the word always. But usually this part stays the same as well, in that it's just I equals 1 to infinity. Or not infinity, n. Sorry, wrong part there. Such loveliness. Okay. The limit as n approaches infinity of the summation from I equals 1 to infinity, which, keep in mind, n is tending towards infinity, right? Now, it says f of x sub I. So it's your function with x of I plugged in. What is my function in this problem? Yeah, my function is right there, isn't it? So my function is e to the x. If we're saying f of x sub I, that's e to the x, but in x sub I, what am I putting in? The xi, which we found to be 2i over n. So it's e to the 2i divided by n times, and then notice it's times delta x. And what was delta x? 2 over n. Okay. What we've done there is we've just taken that and expressed it as a Riemann sum. Okay. So this part right here is our integral expressed as a Riemann sum. The formatting will always be the same. We can pull from this delta x, because sometimes what you'll see them do is they will maybe give you the integral, ask you to pick the Riemann sum from a multiple choice list, or they might give you the Riemann sum and ask you to pick the integral. Okay, so that's what we'll practice a little bit with there. As I said, we talk about that one more later on at some point. I don't remember exactly when it is, but this is just kind of the bare little introduction here. I don't know, you won't see much of any of this in homework right now. Okay? Questions there? Okay. Let's look at example C. Officially, they call this the definite integral, which, okay, it's a definite integral. What we're going to look at is ways to do this besides just fundamental theorem of calculus. So besides doing the f of b minus f of a. Notice on example 5, it says to find this integral, how? Geometrically. Okay. What do we mean geometrically? What is an integral finding? What did we say earlier this lesson? It's finding area, right? So it's the area under the curve. That's what this problem is asking me to do. The area under the curve from 0 to 2 pi. So, in order to do this geometrically, let's sketch a graph. Can you visualize the graph? What's sine look like from 0 to 2 pi? Starts at 0, yep. Goes up. Cuts back through. Goes down. And comes back up, yes? It cuts back through, or it ends at 2 pi. That midpoint, if you recall, is pi. And we start at 0. Now, officially, if we're going to find this geometrically, what do you notice about these two? They're the same, yes? Okay, so what I would call area 1 and area 2 is the same. If we, how do I want to say this? If we just work out this integral as is, and I'll show you here in a moment, we're not going to get the correct answer. Okay? Because what's going to happen is anything above the x-axis comes up with a positive value. Anything below the x-axis comes up with a negative value. So if we actually just find the value of this integral, above the x-axis minus below the x-axis is going to result in nothing, 0, right? Because these are two equivalent pieces. Even though they may be drawn that way, they're two equivalent pieces. So in order to actually, when it says find this geometrically, we want to know what that total area is. Okay, so the area 1 plus area 2. Well, if these two pieces are the same, how can I still use an integral to do this? Okay, find the first one and multiply it by 2. Meaning I can write this as 2 times the integral from what? 0 to pi of sine x dx. And again, this is because it says find it geometrically. If it just asks what the value is, we'd just work it normally. But it's not asking for the value. Essentially, they're asking for what is the area. Okay? So, 2 times, what's the integral of sine? What do you say?
Cosine.
Cosine? No one's going to disagree with them? Did you say negative? Let's say I need someone to disagree with him on this one. Negative cosine x. And this is where I think the derivative of sine is cosine. The derivative of cosine is negative sine. So 2 times the integral negative cosine x evaluated from pi to 0. Okay. Probably should have done this the other way around. Oh well. How talented are you guys? Do I need to write this out, or can you do it just by plugging in? What's negative cosine of pi? Cosine of pi would be negative 1. The negative 1 is positive 1. Minus negative cosine at 0. Cosine at 0 is 1. So it's minus negative 1. Now, I think I did it without saying it. Did you see what I did with this 2 out here? I just kept the 2 out here. I said 2, and what I'll do is I'll go ahead and do the math, and I'll multiply 2 at the end. So 1 minus negative 1 is 2. So the area under one curve is 2. Times 2 makes it 4. And so that area is 4 units squared. Okay. Now, again, I put the other order. I just want to prove to you real quick and put it in writing. If we had just worked this out without looking at the graph. Okay. The integral from 0 to 2 pi of sine x dx. Well, that would be doing, what is the integral of sine x? We already talked about that. Negative cosine x, evaluated from 0 to 2 pi. So the negative cosine of 2 pi minus the negative cosine of 0. Well, what's the cosine? The cosine of 0 we already talked about as being 1. What's the cosine of 2 pi then? Also 1, right? So this is the negative of 1 minus the negative of 1. That becomes negative 1 plus 1, which is 0. So again, what this did is this did the area, the first area, what I called A1, minus the second area that I called A2 is going to equal 0. Okay, and so that's why when it said find it geometrically, they don't want to know 0. 0 is just the value of the integral, but the actual area, if you total these up, is 4. And so just something to be aware of depending on what they're asking. You have to remember that whatever's under the x-axis will count as a negative integral, a negative value. Okay? Okay. Example 6 real quick. Evaluate the integral of 8 minus 2x dx from 0 to 4. Do you want to use like middle school elementary math, or do you want to use calculus? Huh? Elementary math? It is an option. What does an integral mean? It's area under a curve, yes? So think about this. What does the, quote, curve 8 minus 2x look like? A line going down? It's, in other words, I'm asking you, what does the graph y equals 8 minus 2x look like, right? That's what I'm basically asking. And it would be a line with an intercept at, a y-intercept at 8, with a slope of negative 2, yes? And I'm just drawing a line there. Now, where does that intersect right there? If my slope is going down 2 over 1, where is that? 4. What are we asked to do? The area under the curve of 8 minus 2x from 0 to 4. It's a triangle. And this is where I said middle school elementary math. How do you find the area of a triangle? Okay. Daryl says BH over 2. I say 1/2 BH. We're talking the same language, just different forms. So, what are my base and height here? 8 and 4. So, 8 times 4 divided by 2 is 16. So the answer to this problem is 16. Guess what you get if you actually work the integral out? 16. And yes, I'm going to do the math real quick to prove it. Integral of 8 is 8x minus integral of 2x, x squared, evaluated from 0 to 4. Plug in the 4. So 8 times 4 minus 4 squared, then minus the quantity 8 times 0 minus 0 squared. Well, 8 times 4 is 32 minus 4 squared, 16. 32 minus 16 is 16 minus 0. 16 minus 0 is 16. Officially, 16 units squared. There's my proof, right? It's area under a curve.
Say 16 minus 0 was 0.
I think he did say it. It wasn't almost, because I heard it. And then I heard him like, oh, wait.
You didn't say it that loud, but I heard it.
I heard it too.